Welcome back, everyone. It's good to see you. We've come quite far. We've survived until the week before reading week, which is great. Who's got travel plans for reading week? No? No one has any travel plans? No Thanksgiving? Okay, just curious. Right, so there's a little bit of material from last week that I'd like to go over. I'd like to talk a little bit about differentiation, implicit differentiation. Then we're going to move into material about optimization, so maximizing functions. Okay, so this is a little bit of leftover material from last week that we were not able to get to, but I think you guys can handle it, a sort of standard idea.
I got a white hole.
Okay, so we want to find the derivative of z as a function of x, right? So this is like implicit differentiation. We've got some relationship relating these variables, and we want to calculate out the derivative. Okay, so whenever we do a partial derivative, we assume the stuff other than x is constant. So we'll assume that y is constant. And that z is somehow implicitly a function of x. And then we'll differentiate across. Okay, so we take the partial derivative in the x direction of both sides. All right, so this x squared, when we take its derivative, will become a 2x. Plus, we've got a product rule here, so that x will turn into a 1 times yz. Okay, now we've assumed that y is constant, so when we get that corresponding term in our product rule, we get the derivative of y is 0, and then this gives us the derivative we're looking for. Now we can do some algebra and isolate for dz dx. Yeah, sure, question?
So where does the
Right, where does this YZ come from?
Go, where does it go?
Where does it go? That's the important question. It goes into me being sloppy. Yeah, sorry. Yeah, this should come to the right-hand side as well. Yeah. One out of 4 marks for Parker on that one. Okay, yeah, so we bring it over to the other side. Yeah, sure.
So shouldn't it allow me to be X, Y then?
Let's see. Oh my gosh, 0 out of 4 marks. Oh, this is so bad. Okay, wait, okay, so this is good. Yeah. Much better. Yes.
Would it be the same thing if we solve for x first or solve for z first and do the derivative, or?
Yes, this would give the same result. So if you isolated z first
Okay.
and then went through, you get the same result. Yeah, sure.
I don't know what X, Y.
Oh my gosh. I need a coffee. This is terrible. Oy, oy, oy. Okay, I will try and do one example without making a ton of mistakes. My apologies. Okay, so last lecture we found the tangent plane to the sphere at a particular point. And it wound up being really subtle because we had to figure out if we were on the top of the sphere or the bottom of the sphere. Right? We had these sort of 2 tangent planes. We had a tangent plane here and here, and we had to be very careful about where we were. Right? So that was an artifact of solving for z. So now I want to do this without solving for z, and we'll get a sort of a cleaner solution. So we'll get dz dx. We'll assume that y is constant. Now we differentiate through, taking derivatives in x. Okay. And now this is where things get slightly trickier to deal with, is that we've got a chain rule situation happening here where the square is applied to the z. So we get 2z dz dx. Right, so here we were lucky in that we just had a z, so we got dz dx. But here we've got a function applied to z, so we have a chain rule situation. Take this slowly, hopefully it'll work. Okay, we move this guy to the right-hand side. We divide by 2z. Thoughts about chain rule situation? Other thoughts?
Can you explain how did you get, like, how did you do the differentiation?
Right. Yeah. Sorry, there's a lot of mistakes. Here we've got an x squared,
Yeah, so 2x.
so 2x, good.
Yeah.
And then all this stuff here,
Yeah.
right? It's all coming from this term. And it comes as product rule. We've got 3 things multiplied together. So we use the product rule there. So we can do a similar calculation for dz dy. Okay, we'll wind up with the same instance of chain rule, because we've got a squared on the y. So what's nice about this approach is that it gives us our final answers in terms of the actual point that we care about. If we're plugging in this point, right, then we'll get the appropriate slopes just by plugging in the numbers that we have here. Okay, we don't have to think about slanting up or slanting down like we did last week. Yeah, these guys are number 2. Yeah, it's confusing, right? Because the D symbol looks a lot like a 2. These guys are all 2s. Oh my gosh. Thank you for that question. It sounds like it was really illuminating for some people. Yes?
Can you just leave that or just simplify how the expression is that?
Sorry, say again?
So you get minus y over z. Can you just leave it or just have to get explicit expressions to that?
Right. So the question is, can we leave our final answer like this, yeah? Or should we explicitly solve for z? Right? Yeah. So this is a good kind of question to ask. If this is the kind of thing you're uncertain about on a midterm, definitely ask a TA or an instructor. I like these final formats. These are quite nice. If you want to go a step further, and if you want to go one more step, you can go there. The reason I didn't do that initially is now you've got that ambiguity again, that plus or minus ambiguity. Right? So I sort of like this answer because there's no ambiguity, but when you put a plus or minus, then it's hard to discern which one's right. Okay. So now we're going to move into the territory of two-variable optimization. So before we go to two variables, I just want to remind you how we go about things with one variable, and we'll look at the corresponding theory for two variables. So when we want to minimize or maximize a function of one variable, we look at those places where the tangent line is horizontal. Right, so at these points we see that our derivative vanishes. And at those points, we have a chance of being a max or a min. Okay, so we usually call those the critical points.